have Eric Murphy here today. Let me give you a little bit of background about Eric Murphy. So he got an undergraduate degree in English at Eastern New Mexico.
Eastern New Mexico University.
Okay.
And
you all have heard of that place? I've never heard of it.
Has anybody heard of Eastern New Mexico University? Hoorah! How's it's in Portales, New Mexico. Fly speck in the middle of nowhere. It's a great little town.
So after he got his undergraduate degree in English and a minor in math, and decided then to convert and get a master's degree in mathematics. And so he did that. And I guess about the time he finished his master's, he decided to join the military, the Air Force? Air Force. And got a position at Air Force Academy in the math department there for a couple years. And then they decided to send him to get a PhD. So they paid for him to get a PhD. He went to Texas Tech, spent there 3 years, got a PhD in a great subject, mathematics, complex analysis, laces to bubbles, stuff I do. Anyway, and so then when he finished his job, he finished that, his PhD, got a job working for the Department of Defense in Washington, D.C., in the Pentagon. And I met him last year at a math conference in Texas. And, well, we'd met before, but we talked over dinner. And I thought he'd be a great speaker to come talk. So he's here. One other thing is his wife. I met his wife before I met Eric. During the summer, I do a program called an REU for undergraduates to study mathematics for 8 weeks. And in 2001, his wife came here for a 1-week program that I did. And she remembers climbing Squaw Peak. And I remember her climbing Squaw Peak in the middle of the night, which I thought was really crazy, but I guess not for a student. I would never do it. Anyway, welcome Eric Murphy today.
Anyone coming from sea level would remember climbing Squaw Peak. So this, for those of you who haven't taken a pedagogy class, is an attention step. I'm a little intimidated with a crowd, but I hope I have your attention. Dr. Dorff has been very, very kind today in bringing me here. I really appreciate it. It's a really unique opportunity to come back to school. Most of us don't do that. You graduate and you run just as fast and as far as you can. I didn't go to BYU, but I love coming back to school. I remember fondly the things I learned and the ways that I learned them, and I think back on the people I met and the things I did, and all that comes back to me in a really interesting way when I get to do an event like this. So I hope you find this interesting. Now, I have to tell you up front that I'm not going to talk about anything all that terribly classified. Can't do that. I'm not going to jail for Dr. Dorff. I am in the military, and most of what I work on is classified. So that colors what's going to be in the presentation here. The other thing I'd like to ask is that I'm not here, in my mind, to talk to you. I'd much prefer to talk with you. So now I've offered this up. There's probably 100 of you in this room, and if even a few of you have a question, we won't get through all these slides. That's great. I much prefer to talk about the things you want to talk about, not necessarily the things that I prepared. So if you have questions, stop me anytime, shout them out, raise your hand, whatever you feel comfortable with, and I'll try and answer anything that I can. I do come from a slightly odd position, and being in the military as I am, I have a lot of friends in ugly places right now. I have a lot of friends who went to ugly places and never came back. So I'd like to just offer this up as something to remember. Today is Armistice Day. Now we call it Veterans Day. The Great War that ended in 1918 and all the wars prior and since. Just something to remember, something to think about. And with that maudlin, depressing step, I'll move on. So I'm an active duty Air Force major. I've been in the Air Force for about 14 years, almost 14 years. Started as a second lieutenant. And I'm currently assigned to the Joint Staff in Washington, D.C. in the Pentagon. This is a relatively new picture of the Pentagon. Right there is all brand new. Another thing to maybe remember, that's the section that took the hit on September 11th, 2001. Now, technically speaking, I'm an operations research analyst. Anybody know what operations research is? You've heard the term. Operations research has its genesis really in World War II, the modern genesis in World War II. All it really is people with technical skills getting together to solve problems for people who need to make decisions. You find a lot of people who do systems analysis, how to time and motion studies, how to organize a business, how to run an assembly line, things like that. That's all operations research. Now, I don't tell the generals in the Pentagon, well, I don't tell the generals in the Pentagon anything. I'm a major. I answer their questions. I don't deal with assembly lines. I deal with a different class of problems, but the techniques are the same. The mathematical tools that you use, whether it's optimization or it's decision analysis or whatever the case may be, the tools are very similar. Now, I put it in quotes, I'm an operations research analyst because I've never taken an operations research class. I never took a class in linear optimization or nonlinear optimization. I've never taken a class in decision analysis. Those are all things I get asked to do on a daily basis, but I never took a class in one of those things. As an undergraduate, I didn't take a class in a lot of things. Excuse me. But I still get asked to answer questions in those veins. And that's part of what this talk is going to be about. It's not about how math gives you the proximate skills to apply to solve an equation or to integrate some function or to differentiate something or whatever. It's about how math gives you a set of skills that you can apply in a lot of different ways. I never thought I would be doing this. For those of you who don't know, all of the services have operations research positions in them. The Air Force is the only one that takes brand new baby second lieutenants, commissions them, and says, here, go be a mathematician for the Air Force. We're the only ones who do that. And that's what I've been my entire career. The other services take their active duty military members and those who are going to do that kind of work, they come to it much later. First, they're a tank commander or an infantry commander or something of that nature, and then they transition in mid-career to do this kind of work. But all of the services have extensive civilian populations of operations research analysts. Lots and lots and lots of them. The Air Force has thousands all by itself. So from a job availability perspective, I know lots of people when they're thinking about math, I've taken a math class or I'm going to be a math major, I'm going to get stuck teaching high school. Not necessarily. The jobs you can do directly applying your mathematical skills are just innumerable. The jobs that you can do indirectly applying your mathematical skills are also innumerable. And this is one. As Dr. Dorff said, my original degree was in English literature. I read a lot of Jane Austen. I dig Shakespeare a whole bunch. I write a lot of poetry, that kind of stuff. My father's much bigger than me. My father thought that reading Jane Austen and getting credit for it in college was silly. I don't agree with him, but he is bigger than me. So he asked me to study something useful. I object to that characterization too. The ability to communicate effectively, to write effectively, is enormously useful and terribly rare, by the way. But the BA in English I accompanied with minors in math and statistics. I was not a particularly good math student at the time, actually. I almost flunked out of calculus in high school, and would have if my calculus teacher hadn't grabbed me by the ears and shaken me until I nearly died. And in college, I flunked the placement exams for algebra and trigonometry and had to start over, which actually in the end was a great thing. I got really good at those things, and those things are really critical skills. Foundations are really, really important, and so having those helped me a lot. But I was coming to the end of my master's, or my bachelor's degree, and thinking about what I wanted to do with my life. What am I going to be when I grow up? Well, I wasn't ready to grow up just yet. So I wanted to go on and get a graduate degree, but I found myself not enjoying English and the study of English quite as much. And suddenly, I'd gotten far enough in math, just far enough, that this whole world was opening up. The connections between classes. I can remember very distinctly in my senior year, taking a probability class and a calculus class, and the two were feeding off of one another in a way that I'd never had yet in math. And suddenly, I started seeing these connections everywhere, and thought, well, that's something I can do. I can get into this. And the math department at Eastern New Mexico was kind enough to take a chance on a burgeoning math nerd, and let me go on and get a master's in math. Now, coming to the end of my master's degree, I had lots of opportunities. I applied to Texas Tech University then and was admitted, and thought about going on and studying statistics. Probability theory was something I was really jazzed about at the time. Still am, just not in quite the same way. But I was also really, really tired of eating ramen and macaroni and cheese. I wanted a house. I was sick of living in a one-room shack. And I come out of a military family. My grandfather is a career, or was a career Navy officer. My father was a career Air Force officer. My brother was a United States Marine, is now in the United States Navy. And the Air Force seemed like a pretty good gig. And they do things like fly airplanes. That's just cool. Those guys are awesome, right? They're the cool kids. And they're the people I grew up with my father in the military. I grew up around these flyers, these fighter pilots, and these really cool guys. So I thought, well, heck, that could be all right. And then pay me. So can I get in? Yeah, I did. I did get in. Unfortunately, I made this, at the time, it felt like a mistake. In the end, it's not. I wrote on my little dream sheet, what do you want to be when you grow up? I'll do anything the Air Force wants me to do. They made me a mathematician. And sent me to Kirtland Air Force Base in New Mexico to do something called operational test and evaluation. When the Air Force, or the DoD in general, is going to go buy something, we're going to spend billions of dollars developing a new airplane, or millions of dollars developing a little radio, or anything at all, we're required by law to put it through a process called operational test and evaluation. They give it to somebody like me, they hand me a $3 million radio and say, go figure out every way this thing can break, and write it down. Whoa. I get to swing this thing around in the woods and bang it against a tree and see if that works? You bet. I actually did it. It didn't break. It's probably a good thing. I wouldn't be here. Most of the systems I worked on were small systems, and actually that's a really good thing, because it meant that the acquisitions were really fast. So as a mathematician, I got to design the experiment by which we were going to test this thing. How many times do I need to send a message to make sure that the message works? Under what conditions do I need to send a message to make sure the message will work? What's going to give the decision maker who's going to sign on the dotted line, write the check to buy 100,000 of these radios, how can I make sure that I've captured the risk in his mind so he can be comfortable in making that purchase? How can I communicate to him that I've done all my homework and that I've done it right? Yeah, sure.
Did your English degree help you in that?
Absolutely,
okay.
Absolutely. I wouldn't trade the fact that I have an English degree and read a lot of Shakespeare for anything.
Okay.
If nothing else, I have a big vocabulary. It gets me in a lot of trouble, but absolutely. An English degree, here's a weird myth. Okay, let me throw out this weird myth for you. English is creative and math is not. Has anybody ever heard something like that? Or, I can do English, but I can't do math. Or I can do math, but I can't do English. Anybody heard that? Yeah. Don't say it where I can hear it. You can do both. They're different skills maybe, but English can be very, very rigorous. You have to be rigorous in a lot of ways. Thinking through how things relate to one another and what kinds of statements you can make and justify reasonably, that sort of deductive process of A implies B, which implies C, and gets you to some kind of conclusion. Constructing that argument is a mathematical process, and you do it everywhere in life. You do it when you're writing a paper in English, you do it when you're working in biology, you do it when you're a lawyer or any other thing, for that matter. You do it when you buy a car. I need this, it comes from that. The comes from this, but it doesn't come from that, therefore my choice is narrow, and that's how you live your life. But at the same time, math is an incredibly creative process. It eventually, it's not always. Calculus isn't always all that terribly creative. Sometimes it's fun. Yeah, I'm an unrepentant math nerd. It's fun. I love integrals. The puzzle of an integral is great. But they're both valuable and they feed off one another, and I wouldn't trade either one for the other. Any other questions? Yeah, please.
Oh, was your design of the experiments as this radio mainly based on like physical properties, or?
Well, it's based on a lot of things. One, you start with a design document. Somebody's going to tell you what this thing is supposed to do. I'm supposed to be able to use it in these environments to send these kinds of messages or talk at this range. And then the design of the experiment is, in a constrained cost environment, I'm not going to get to do anything like a full factorial, every possible thing, test it out with lots and lots of samples. And so it's figuring out which things are critical paths and which things aren't, and which things are key in the performance and which things are desirable in the performance, and how they relate to one another. That relationship set is as important as the individual elements. The interesting in between is where all the fun happens. Did that answer your question? Sort of? I can try some more.
Well, I guess, did you do the experiments or design the experiments?
Yeah. So you decide there's an exercise. For example, I was working in combat search and rescue equipment, a radio that allows you to take somebody who's been shot down over enemy territory. You can find out where they are, find out if they're okay, and go get them. Okay, all important things. Integrating GPS into this problem, integrating voice into the problem, multiple frequencies that are difficult to detect, so an adversary can't do direction finding, find out where you are and come kill you, or better yet, capture you and put you in a prison and parade you around for people to see. So you figure out a way to test that. You go off to an exercise. Say we did a lot in Alaska or a bunch in Arizona, where there are pilots who are doing flying exercises, where there's helicopters in action, and you can set up a scenario where I drop a person in the woods at an unknown location. He has to tell people where he is. They have to go get him. He has to use that radio in the operational context for which it's intended, and I make all that happen. And then you get a bunch of data back, and you do some data analysis on it, and use that to convince the decision maker to buy it. Better answer? From there, I went to the Air Force Academy. The Air Force Academy is just a great gig. It was a wonderful place. To get to teach math, and teach math to really small classes, and to be a part of people growing up is a real privilege. And I enjoyed my time there immensely. I spent 2 years there, and they selected me to go to Texas Tech to get a PhD in math. I studied complex variables. How many of you have taken a complex variable class? Take another one. Complex variables is awesome. I thought it was anyway. I love the visual element of it, and I love how elegant it can be. It doesn't mean that the others aren't. It's just this one spoke to me, and I got along with my advisor, which is an interesting and really important thing. The advisor you pick is really critical. But I went to get a PhD in math. And if you want to know what a math dork I am, I built myself a math family tree. Yeah, I'm a nerd. These are all my ancestors, And the other really cool thing about a math degree, you might just meet your wife or your husband. My wife was enrolled at Texas Tech at the same time. We got there at the same time. I graduated a year before she did. I'm better than she is. This isn't on film, is it? But that's my wife. I put this in because it is on film, and I know she's going to see this, and she's going to kill me. It's awesome. So we both went to Texas Tech. She's also a math PhD. She did numerical analysis, stochastic partial differential equations, and numerical methods for solving them. I did complex variables, a field called circle packing. And I'll talk about that in just a second, a little bit. What we did isn't really all that terribly important, except that neither one of us now use it in a direct way. I don't do complex variables. She doesn't do partial differential equations. She does lots and lots and lots of math, but she doesn't apply the thing that she studied in enormous detail. What she did is she learned a set of tools a set of techniques, a way of thinking about the world, a willingness to spend time on a problem and chew on it until it dies, she takes that into her job. I might do the same. From my time at Texas Tech, I went off to the Pentagon, as Dr. Dorff said, to a place called Air Force Studies and Analysis, and I was there for 4 years and transferred to the Joint Staff. I worked for the chairman of the Joint Chiefs of Staff, Admiral Mullen, sort of, about 3 steps below him, but I work on the Joint Staff. The way that the military is organized, just to give you an idea of the kinds of things that we do or the questions that I get asked, the military is organized sort of along 2 branches, with, by law, the chairman of the Joint Chiefs of Staff at the top. And the chairman, his job, his primary job, is to act as the principal military advisor to the Secretary of Defense and to the President. If they have a question about the military, he's the guy that asks. And that's a pretty broad mandate. It can be anything that they ask him. Should we buy this or should we not buy this? Is that plan for an operation that we're going to conduct good or not? Should I send this material to a foreign country or not? Another one that's hot in the press right now, don't ask, don't tell. What are the consequences of the repeal of don't ask, don't tell? These are things that fall inside his bailiwick. Underneath him, he has 2 branches, essentially. On one side, you have the services. The services, what they do is they organize, they train, and they equip. Their job is to buy stuff, train people to use that stuff, and then give that stuff and those people to someone else to employ it. The components of the combatant commands. Central Command has charge of Southwest Asia, Iran, Iraq, Afghanistan, that area. PACOM has the Pacific region, EUCOM has the European region, and so on. They're the ones who actually employ forces. And at one time or another, I've worked in some capacity for each one of these. And the kinds of questions you get asked are different in each one of those. I just spent a lot of time thinking through some of the don't ask, don't tell kinds of questions. The organize, train, and equip. How much of what should I buy and why, and what's the risk if I don't buy it? Spend a lot of time doing that in here. How should I employ it? Where should I employ it? Should I ask for something else? Is this airplane good enough? Or should I have this airplane? What should these airplanes have on them? Should I get more UAVs or less UAVs? Does it matter? Those kinds of questions live over here. And I've worked at one time or another in each one of those. In the end, my job is to learn how things work, to design the experiment, figure out how the pieces relate to one another, and explain that to others in relation to other things, often quantitatively, not always quantitatively. The process here is a logical process. It's breaking down a problem. Analysis means to take a problem and break it up into little pieces. It's where the word comes from. And so you take that problem apart, all its little constituent pieces, figure out how each one of those pieces work alone, then figure out how those things work together, figure out how the system works so that you can understand what happens when you change an element in the system, and then explain it to somebody. And that's the English major in me. I do a lot of writing. Some of it for publication, but mostly it's internal writing. Now, how does my degree apply to that? I've already hinted at this. Really, it doesn't. My dissertation is called Discrete Conformal Approximation of Complex Earthquake Maps, which doesn't really mean anything to anybody except about 4 people in the world. It's a very weird discipline. But it's applying a thing called circle packing, which is really, really cool. And if you want to talk about it, we can sit down after this, and I will go on and on and bore you to death. But what does that have to do with what I do? Almost never. I almost never use it. But that's not really the point. The point, and this is something that not everybody would necessarily agree with this. I'm just relaying an opinion of mine. My math training is all pretty pure. It's probability theory. It's functions of one complex variable and real analysis and the theory behind it. It's topology and algebra and the theory inside of it. It's not really applied math, which is what operations research is a branch of applied math. But I think that's good. I get asked this question all the time, and I have to explain to a colonel, don't worry about it. That's not the point. One of the things that a pure math degree gave me, I think, is I get tools, I know how to do math, and I get those tools without bias toward a given tool. If I know how to do linear optimization, and that's what I did all my research in, then every problem that comes along starts to look like a problem that maybe can be applied or attacked with that kind of a tool. And those biases are insidious and they're problematic. They're really hard to fight. So one of the things about a nice pure math degree, at least from that I don't get that. There's also, and I've talked about this a little bit, math has a peculiar rigor to it that other disciplines don't have. At the end of a math proof, it's true. You know it's true. It's true within the axioms, but mathematicians talk about their axioms. You know what they are. You know what your underlying fundamental foundational assumptions are. You can enumerate them. And that sort of systemic body of thought is something that most disciplines don't have. And math talks about it. We take all that stuff out and we hold it in front of us and we turn it around and we talk about it with each other. And that kind of rigor doesn't exist anywhere else, really. A little bit in some places, but math is pretty peculiar in that way. The deductive method and the requirements of the deductive method are much more stringent in mathematics than they are everywhere else, in my experience. If you disagree, please throw rocks. Thick skin and hard head. The other thing that math does that's nice is math is, at least in the way that I learned it, is very abstract. What mathematicians do is they build models of the world. And then they take those models, which are abstract representations of things, and they play with them. And they figure out how those models work. And then they try and relate, sometimes, those models back to something else. And relate those models to other models. And talk about why those relationships work or they don't work. But that kind of abstraction is really important to what I do. To answer a question about whether I should buy forces or not buy forces, I have to be able to build a model of the world in which I can evaluate the goodness of those claims. And if I'm not able to abstract out of the minutia of the elements inside the problem, if I can't think about it as a system that's not the individual things, but some sort of representation of those things, then I can't do my job. And I think that math has really done a great thing for me. This does come with a problem. These kinds of thinking. In math, we get accustomed to the idea that there's a solution. We get accustomed to the idea when you take a calculus class, I can differentiate this sucker, and there's an answer. And I can plug in a number, and something comes out. And I know what that something means. And I can solve the problem. If I can state the problem, I can solve it. I know I can solve it. Now, it may be hard. Or it might be one of those things where you come back to Gödel's theorem, but you know that's stuff we don't talk about in public. Where it's not provable inside the system, but you can still talk about it inside the system. But we get accustomed to the idea that every problem has a solution, and I can show it to you. And once you see the solution, you'll recognize it. Most of the problems I deal with don't look like that. They don't have solutions, or I can't tell what the solution is going to be, or tell you what the criteria for the solution is going to be ahead of time. Or I can't formulate the problem well. I have to deal with a lot of things that aren't well formed. They're fuzzy. They're what Russell Ackoff called messy problems. He was dealing with that in the context of social messes, social dynamics. But the problems I deal with are messy. It's hard to state the problem, and once I've stated it, it's hard to solve the problem, in many cases because the solution doesn't exist. Yeah? What?
Are these problems like least squares where you find the best approximation?
They can be. They can be. And in fact, those kinds of tools, we use them all the time. We do linear programming, we do nonlinear programming, we fit least squares curves, and we use them to interpolate or to extrapolate and come out with an answer, and we give that to the decision maker. The problem is that in order to do those things, I have to be able to tell you what the decision variables are. I have to be able to tell you how the decision variables interact with one another. I have to be able to tell you the environment in which they're going to interact. And all of those things, all of those simplifications, all of those abstractions, take me away from the real world where the solution is going to have to live. And if I can't characterize effectively what I've done in the abstraction, then I've got a problem without a solution. I've got a solution, but I can't tell you whether the solution is really the right one or not. There's an extra problem that I'll talk about in a second. It's not just me who gets to vote. So if I do something, think about warfare, I do this. I play Alexander, and I send my forces in some sort of pincher maneuver at Gaugamela. And the Persian king, he gets to respond. And he's not going to respond in the way that I tell him to respond. Darn it, that was the optimal solution. I'm supposed to do this. Why didn't you do what I thought you were going to do in response? Now I'm going to lose, or something like that. I really should have told that story from the Persians' perspective, since they got annihilated at Gaugamela. But you get the idea. Unless you can characterize all of those things and include all of those things in your model, then you don't have a solution. A real solution in the way that mathematicians think about solutions. So there's great value, but with great value comes great responsibility, or what was it Peter Parker said? Sorry. I told you I'm a dork. I can't help it. I haven't made any Star Trek references yet. So now, where does my degree apply? Almost never. I say almost never because I was able to squeeze that sucker in once. I was able to squeeze circle packing into a problem. Circle packing, what you do is, y'all, does anybody know what the Riemann mapping theorem is? The Riemann mapping theorem? Okay. Functions of one complex variable. The Riemann mapping theorem says if I take some simple closed curve that defines a region in the complex plane, there exists a unique map that will take this thing over here to the unit disk that will fix one point at the origin and give you a rotation. Okay, so it's a fun theorem. Really cool stuff. Riemann of the Riemann hypothesis that you may have heard of. So circle packing is a way to calculate these transformations. And I was using this to talk about spaces in which unmanned aerial systems operate. If they're going to wander through a space looking for stuff, what effect does the shape of the space have on the way that they wander through that space? It's a random walk problem, a Markov process problem. And it's critically tied to the shape of the space. If you've got really isolated regions, like that little arm that sticks off the end of Afghanistan, and you're doing sort of random processes, it's hard to get there. And once you get there, it's a little hard to get out. And so figuring out what hard means, I applied some methods of complex variables to do that. And you wouldn't believe the look on the 3-star's face when I put this in front of him. I actually had math. I left all the math stuff out of this, but boy, that was fun. His eyes got really big. You did what? Son, do you know what that means? Yes, sir. All right, that's fine. Good, I trust you. Don't ever do that again. But I have used math in operational contexts in the past. So you'll recall I told you that, that there's one arm of the DoD that what we do is employ forces. That's what the people in the Middle East are doing right now. There's a place in Qatar called Al Udeid Air Base. And at Al Udeid Air Base, you've got the Combined Air Operations Center. That's where the Air Force controls the aircraft that are in the theater, tells them where to go, tells them what to do, decides where they fly on a given day, things like that. I worked for the 2-star who ran the place. And the way that we were deciding which airframes go to which places and what they do when they get there was giving us real problems. It was giving us a terrible time. We're giving him a terrible time. Wasn't giving me any problem at all. I was just watching it happen. But how to characterize that problem for him and help him to think through that problem, how to frame it, became a task that fell on me. And what I threw at him was a little piece of game theory that was popularized or first explored in the 1800s, but then by William Forster Lloyd. But then in Garrett Hardin in 1973 wrote a paper about it in Nature or Science. I always get those confused. What the tragedy of the commons says is if you've got a scarce resource and lots of people competing for that resource and the benefits are individual, if I get a piece of the resource, that benefit all comes to me, but the costs of putting that resource out there are collective, like grazing sheep on a common. The sheep is mine. I get the wool and the milk and everything else that comes from the sheep, but everybody's got to maintain the common. And every sheep I put on the common takes away from your sheep's ability to use the common. The English commons is where it comes from. So phrasing the allocation of air power in that context amounted to sort of pulling a hand grenade and throwing it on the table in front of the 2-star and all his colonels and watching them fight with one another for an hour, which was really fun. But it was a way of thinking about the problem that he hadn't done before. Now, I've never taken a game theory class, ever, but I can read game theory. I can pick up von Neumann's book and I can read it, and I can understand the math inside of it. This is actually a picture we showed him, by the way. Notice there's no math on the side. Take all the math off because I understand the math and he trusts me. It didn't give him a solution to the problem. I wasn't trying to give him a solution to the problem. What I was trying to do was to give him a framework within which to argue about the problem with people who could give him solutions to the problem. And that was actually probably the most, well, it's not the most interesting thing, but it's the most interesting thing I can talk about that I did while I was over there. What else have I done? This is a paper. Yeah, please. Should I go back?
No. I was just wondering, like, in your job, would you ever be deployed, or is all
Yeah.
your work
Yeah. That's me at IUD. That's the helicopter that was following us from Kabul to Bagram Air Base. This is really scary, by the way. Flying an helicopter in Afghanistan is non-trivial. Hey, no joke. We're taking off. We're leaving Kandahar, not Kandahar. I'm sorry. We're leaving Kabul to fly back to Bagram Air Base so that I can go back to IUD and sit in my Hawaiian shirt and enjoy myself. Because you should never, ever, ever forget the deployment lessons learned from MASH. We're taking off, and darned if the helicopter in front of us didn't start shooting flares out the side. It scared the snot out of me. It was a test. There wasn't anybody shooting at us. But, oh, Lord, it got my attention. So, yes, there are opportunities for me as an operations research analyst, either a civilian or a military member in the Air Force to deploy. Right now, there's 15 positions for us that are deployed in Iraq, in Afghanistan, and some other places. But I would go back in a heartbeat, and I volunteered for everything that ever comes along. So I guess it depends on who you are and what you want out of life. That's where things are going on. And so, yeah, I would go back in a heartbeat. They keep begging, they keep telling me now. Another problem that we worked on, and this comes into the area of acquisitions. Should we buy a particular kind of system or not? And if we should, what should the characteristics of that system be? Specifically here, what we were looking at is airborne early warning. You guys know what an AWACS is? It's that 737 with a big spinning dome on top. Its job is to look at airspace and see things coming in. Okay? So it's that kind of problem. How do we defend the homeland? There's a requirement stated for us in what's called the Joint Requirements Oversight Council says, you will do this, Air Force. So how do we do it? We have to defend the entire United States from mud to space, from homeland or from air and cruise missile attacks. So how do we do that? Well, we did an analysis. This is an unclassified representation of something that we did that was classified. And if you're really interested, you could probably Google strategy alternatives for homeland air and cruise missile defense and find the paper that these pictures came out of. But we had three basic things that we were trying to do. Not to solve the problem again. What we were trying to do was to help our leadership understand what the critical components were and help them think through the problem in a way that made sense. So first, what does it mean? We use game theory here because it's sort of a classic attacker-defender kind of thing. It's the adversary is going to take an action, and you're going to take an action, and you can't predict each other's actions. And so how do you act in order to minimize the damage that the other guy can do to you? It's a classic game theory kind of representation, so we went at it that way. But in order to describe a game theoretic construction, you have to be able to give value to the things that are in the environment. And very often we want to put constructs of value that are really, really precise. I run into this all the time, where it's a strict valuation, it's a strict order, that everything is either greater than or less than everything else, that you're not allowed to have equality. The reason we do that, one of the reasons we want to do that, is because it gives us a feel for precision, a belief that the answer is the answer. The answers don't exist, though, in a lot of ways. I mean, it's easy to tell the difference between New York and Wilmington, North Carolina, unless you happen to live in Wilmington, North Carolina. But it's really hard to tell the difference between Rochester and Syracuse. for example. So valuation isn't really about strict valuation, it's about tiered valuation. And that's a really difficult concept to communicate to people. One of the reasons is because as soon as you do that, you've explicitly said that there's no answer. You've built a system where you're going to get lots and lots and lots of equivalent answers. And people don't like that. When they're making decisions, they want the decision to be given to them and to have the imprint of authority. And it's kind of a myth. The other thing that we were trying to do is to convince them that if you had two things to defend, say New York and Washington, D.C., and you only had one system to do that defense with, they would say, we kept getting this over and over again, that, well, I defend Washington, D.C., and then they kill New York, so that's not a capability, because I'm just going to lose New York. That's just crazy. Well, that's not true, necessarily. You don't have to choose that way of going at the problem. What that general was doing implicitly was choosing what's called a pure strategy, and we were trying to convince him that, look, there's all kinds of, in fact, infinitely many, other, uncountably infinitely many, yeah, I'm a nerd. What do you want from me? Mixed strategies that get you some value. Now let's argue about how much value they get you and whether that's enough. Let's quantify the risk in some way. Yeah.
I was going to say, you have the word Nash defense. Are you working like with game theory with the Nash equilibrium?
Yep. So what you see here is an effectiveness metric that we described. This is the effectiveness metric that comes from the Nash equilibrium solution. Okay. And this is sort of a greedy defense where you just pick the most valuable thing. That's exactly what it is. The other thing that we were trying to convince them of is if you're going to spend money, don't spend it stupidly. That if you've got one sensor and he can see X distance, say he can see about 75 miles, then he can defend a certain amount. But if you're going to invest money in a new radar and you can't cause him to jump past that discrete distance that's going to allow you to defend something else that's interesting, then don't spend your money. It's a waste of time. Spend it someplace else. This was actually a really huge problem in this scenario. And this chart helped us a lot. Just being able to draw the picture sometimes, especially if people don't like math, being able to draw the picture will get you an awfully long ways. So again, I never took a game theory class. Another example. This is in the force structure question. How much of what to buy? How much intelligence, surveillance, and reconnaissance stuff do I buy? How many C-17s do I buy to move stuff around, and air refuelers, and F-22s, and F-35s, and so on? How much of those things do I buy? The way that this problem gets phrased, almost in its statement, how much of what do I need to accomplish a set of tasks? It's almost phrased as an optimization problem. You've got a set of decision variables. How much of what am I going to buy? To do what? A set of objectives within a set of constraints. I can only spend X amount of money because Congress doesn't like us very much right now, and so they keep taking our money away. They're really smart people, that Congress. So how much of what do I buy? Now, I can make two choices at that point. I can either represent this system as a linear system, in which case I've got all kinds of cool linear optimization techniques that work really well, and I can find a solution and it'll be on a corner, or you'll get some degenerate solution that follows one of the lines. Or I can do some sort of nonlinear solution. The problem with nonlinearity is it makes the problem hard, whatever that means. Working in the Air Force, probably going to get in trouble for letting this secret out. This is what they do. They do linear optimization. And this presentation was us talking to ourselves as sort of self-critique. It's, look, numbskull, maybe there's another way. And if there is another way, is it a better representation of the problem? And if it is a better representation of the problem, what are the consequences if you're doing it wrong? When I yell at people like that, they get mad at me. I don't yell at the Pentagon. I'm just yelling at you, because it's fun. So just drawing those pictures. This isn't fancy math that we're doing. What we're trying to do is take the problem apart, break it down into its constituent pieces, figure out how the pieces talk to one another, and think about what the consequences are for different interpretations of how those things talk to one another. That's math. I haven't really done fancy math here, but the thought process is mathematical. And any one of you could do it. Okay. I think I've got one more example. Here's one more, and then I'll part ways. Now I've got two more examples. I take that back. So the force structure problem that I just represented, in order to do that optimization, you have to be able to describe the environment in which you're going to operate with perfect precision. I have to know exactly what the bad guy has. I have to know exactly what I need to do to make that bad guy go away or quit and go home. I need to understand it exactly. The problem is that that assumption all by itself, that axiom, that underlying construct is flat wrong. We have no idea what the adversary is going to do. We have no idea who the adversary is going to be, really. So optimization in this context is inherently problematic. And I didn't make that up. Eisenhower said that in a press conference he gave in 1955. So in the context of a problem I was working on, a surveillance and reconnaissance problem, and this is where I got to apply circle packing, by the way. It's the talk that Dr. Dorff saw in Waco that got me here, much to your chagrin. I started with that. And asked myself, how can I take away as many assumptions as possible? How can I take away as many of those assumptions on which my answer relies as possible? And I came to an idea about random walks. And then I took those random walks and I did some things with them where I constructed a model where I have what amounts to pheromone controls. This is where the control theory stuff that I've been doing comes in. Using pheromone kinds of activity to control the way that UAVs move through a space. And part of the reason that this is important, and part of the reason I got any traction at all inside the Pentagon, is because we're really rapidly moving from an environment where we've got a handful of systems that are relatively big, and you fly them actively. You've got a hand on the stick, and you tell it to turn left and turn right. You tell it to go up and go down. That there's a guy, usually living stateside, and flying at remote control. The problem is that these things are getting really, really small. That size comparison is real. Little self-contained flying things, or crawling things, or floating things, or just stationary things for that matter, that are going to be in our environment. And you're not going to be able to control those in this way. You can't. Already, to control one orbit of Predator, it takes 179 total people to do that. So if it takes 179 people and I go from having a handful of orbits to having thousands or hundreds of orbits, then I've got real problems. So finding new ways to control those things is really important. And this was an exploration of how to do that. If you want to know the details or talk about the details, I can certainly show them to you. I have them with me. I'm just not going to talk about them today. The other thing that I'm doing right now, this is a lot of fun for a dork like me, is taking that idea that my enemy gets a vote, that I'm going to do something, and then he's going to do something, and then I'm going to respond to him, and he's going to respond to me, and exploiting that. Thinking about this entire problem not as a point solution in an optimization, that this is what I need, and this is where I'm going to go, and turning it into an evolutionary problem, using genetic algorithms to describe force structures and goodness in force structures. How much of what do I need? And let the systems talk to me about how adversaries and protagonists interact with one another. The really interesting thing, and this is as close as I get to math in the rest of this, explicit math, is that as soon as you start talking about evolutionary systems, biodiversity or concepts of biodiversity become really important. Because if something happens that's unexpected, like 9/11, and the world changes, at least the way that the DoD, the Department of Defense, thinks about the way the world changes, or the Russian Empire crumbles, and you wind up with a dissolute Soviet Union, the world changes on you. Everything changes, and all of your solutions don't work anymore. How do you make sure that you've built a system that can handle that? Well, that's a biodiversity problem, and so I'm applying techniques from entropy and from complex systems and biological systems analysis to try and capture some of that. Okay, so those are all the examples of the kinds of things I've done. I only have really 3 pieces of advice. One is to learn how to think and communicate persuasively and non-technically, be able to write, be able to speak, be able to communicate non-technically. Because if you go out into the world, say you go to a Goldman Sachs, or you go to Walmart, and you're a mathematician, an operations research analyst or something, and you're actually going to do math for them. You're going to design their distribution system or something like that. The person you have to convince that your answer is right is not a mathematician, probably. They're not going to buy it. The general that I was deployed with, he was a PE major, not a mathematician. Great guy, smart as all get out, but not a mathematician. And I couldn't communicate with him like he was. So if you're going to communicate to your audience at some point, or if you're going to go into a world where you're not actually doing math, equations and variables and functions and things like that, nothing you do is going to be mathematically technical, and so you're going to have to deal with that. The other thing that I would suggest is that you get comfortable with ill-posed problems, with indeterminate problems. In the real world, most of them are. At least that's my experience. And you want to get comfortable with that. And this goes to a certain extent with those other two. Keep your focus as wide as you can. How many of you are graduate students right now? Okay, I've got one hand raised. So the rest of you are undergraduates, right? You don't have to know what you're going to be doing 10 years from now, right now. Okay? I was an English major, and I studied a little math and statistics, and I use both of them. And I read history, and I use it. And I read science and popular science literature, and I use it. It gives me ideas, things that I can apply. You never know where the idea is going to come from. So right now, I have this bit of advice that I would suggest that you not concentrate too heavily on one thing. Now, Dr. Dorff might not agree with me because he wants you in his complex variables class, but that's my take. And that could be a mathematical thing. Don't pick one discipline and dive into it as deeply as you can. You're an undergraduate. That's not what undergraduate work is about. Then these things that I think are the reason math is good for me. One is its special rigor, and it applies anywhere. Two is that abstraction is powerful, and nobody teaches that like math. Nobody teaches that the way math does. And the last thing is that math education makes it possible to learn math. Learning biology doesn't teach you how to learn anything but biology. But math is used in biology, and in statistics, and in physics, and in the social sciences. It's used everywhere to one degree or another. And if you can read the math that's going on in it, then you've got a window into it that other people don't. And that's been huge for me. So I hope I haven't wasted your time. Does anybody have any more questions? I think Dr. Dorff is standing up here so that you can kick me out of the room.
So let's thank Eric first.